Chapter 4, Part B, Compatibility of Deformations. In this example, we review a problem which includes an aluminum post shown which is reinforced with a brass core. If a 9 kilopound axial force applied to a rigid cap, which you can see here, and that rigid cap work as a distributor of forces between the outer cylinder of aluminum and as well as the brass core. Mhm. If the specification of material is provided, like we know the modulus of elasticity for aluminum is 10 times 10 cube KSI, and the modulus of elasticity of brass is provided to be 15 times 10 cube KSI. We want to know what the average normal stresses are in both materials. Let's approach the problem. Solution. So first of all, we do need to develop the equilibrium equation for forces, like sigma Fy equal to 0. In that case, the internal forces of brass and outer part should contradict the uh, 9 kilopounds axial force which apply to the cap. Mhm. And because the material are twisted with each other, they are inside each other, and we do know from the compatibility of displacement that they have to, due to due to the rigid cap, there is a cap as a distributor of forces between the two materials. So in that case, they move with each other. So we do know from the compatibility of displacement due to rigid cap, delta aluminum is equal to delta brass. And the last equation is load displacement, like uh, what we learned from previous parts, which delta is NL over EA. So axial force of aluminum times the length. The length is equal for both of them, 1.5 feet. So it cancels out each other. Over area of aluminum times modulus of elasticity of aluminum should equal to force of brass over area of brass times modulus of elasticity of brass. If we do the mass, it gives us a parametric relation between two forces. And from the one, we do know the summation of forces should be cancelled out by the initial axial load at the very top. Mhm. Knowing this, and just replacing the numeric value in our uh, solution, it gives us a numeric value of FAL is force of aluminum is as 2 as force in brass. Hmm? And from equation 1, we do know both of them are equal to 9. So it simply gives us aluminum goes by 6 kilopounds, and brass is going by 3 kilopounds force. By knowing the forces, calculation of stresses is already pretty simple enough. So the average normal stresses in both materials, aluminum and brass, is going to be just their forces. For example, sigma aluminum is nothing but 6 kilopounds over the area of outer cylinder, which stands for the aluminum, and that's gives us a point 637 KSI. And do the same for brass, gives us a numeric value of 3 kips over pi times in parentheses 1 inch squared gives us 0.955 ksi, kilopound square inches. By a simple comparison between the two materials, you can easily see how the stresses in the inner part, which applies uh, the to brass, is higher than the outer cylinder, which includes a aluminum cylinder. And again, sigma AL is 0.637 and sigma brass is 0.955, which you can easily see this is uh, higher than aluminum. Note the stiffer material goes by larger stress. So by stiffer we mean the material which with the higher modulus of elasticity. So sigma of brass is higher than sigma of aluminum. Mhm. That's due to brass is stiffer than aluminum, and by stiffness we mean the modulus of elasticity of brass is higher than aluminum. Thank you.